Hi everyone and welcome to this lecture. In this lecture I want to go over some examples of Gram-Schmidt orthonormalization algorithm. So please watch my last video. In the last video I'll explain the process and where that comes from. And again, what's the goal? If you're given a basis in Rn, a basis for a vector space. So that's a basis. We want to take that basis and make it an orthonormal basis. That means orthonormal basis means a vector set where all the vectors, first of all, they have to be linearly independent because it's a basis, and they have to be orthogonal to each other. Also, the magnitude of each vector has to be 1. Now going over the process, just reviewing that, you start with W and you put that equal to V, what you call that V1, and you want to find a W2 that is perpendicular or orthogonal to W1. So it's just V2 minus the orthogonal projection of V2 over W1. And the general formula, you can say Wi is V sub I minus the sum j equals to 1 to I minus 1, and that's Vi Wj and Wj here and Wj here, and you do it with each vector, so 1 by 1. When you do that, then you can find your W's. However, this is an orthogonal set. W's are orthogonal to each other, but they're not normal vectors. Then the last step in the process is to normalize each W. Then once you do that, then you get a set of vectors that are orthogonal to each other, and the norm of each vector is 1. And in the next lectures, we're going to see how useful this process is. So in W, let's go over this little note and I'll do the example and you're going to see that better. So you always get W1 to be V1, which is the first vector in your set right here. Then you start the process. W2 is going to be V2 minus, so the orthogonal projection of V1 over W1, and then when you do that, you know W1 and W2, they're going to be perpendicular or orthogonal to each other, and W3 is just that's the summation. And please be patient with the example, you're going to see that. So you take V3 and you find the orthogonal projection of V3 onto W1, and you find the orthogonal projection of V3 onto W2. One thing to notice that W3 and W1 are 0, and you can just use this. The dot product of these two vectors is going to give you 0, and therefore you know they are orthogonal to each other, and same as W3 and W3. But let's do an example because it's going to be much clearer with an example. You can see the numbers. So the example I took, it's in R2. You're given two vectors, V1 and V2. So you call W1 to be V1, and that's the first vector. The second vector is the V2 minus the orthogonal projection of V2 over W1. And you know that's what you use, that's the formula. one thing, you know that norm of W1 squared is just W1 dot. W1 is much easier to use that. So you take V2 minus norm of V2, no, minus the vector V2 dot W1, which was just V1, and then that's over W1 dot W1, which is the norm of W1 squared, and that's times W1. Just notice this is just a number. If you do the calculations, that becomes 1/2 times W1, and what you have is 0, 1 minus, and then this is 1/2 and 1/2. So if you calculate that, you get negative 1/2 and negative 1/2. So our base B prime, the vectors W1 and W2, the first vector is the same, which is V1, and the second vector is W2, which is negative 1/2 and negative 1/2. However, we shouldn't stop there because the magnitude of those vectors are not 1. So you normalize each vector. So if you do that, then I called the last vectors u1 and u2. So this is an orthonormal basis. If you find the norm of this vector is 1, the norm of that vector is 1, and this norm is, if you do these vectors, if you do u1 dot u2, you're going to get 0. Just to see what's going on here, we started with v1 and v2. These vectors are not, these two vectors form a basis in R2. However, they're not orthogonal. Then when we do the process, we get these black ones, W1, W2. So these are, as you can see, they are orthogonal to each other and perpendicular to each other. Then you normalize them, then you get U1 and U2, which is right here. And these vectors, as you can see in the drawing, they are perpendicular or orthogonal, and the norm of each vector is 1. Let's do 1 in R3. So we start again with 3 vectors. The first vector W1, you just call it V1. You take that vector. The second vector is V1 minus the projection of V2 minus the projection of V2 over, and that should be W1. And that's going to be V2 minus the projection of, again, same thing, V2 over onto W1. And you can use the formula. That's the orthogonal projection formula. So let's go ahead and find it. You substitute, this is our V2 from here. And that's minus, that's a V2 dot V2 over W1 dot W1, which is right here. And again, this is always a number. So if you do that, you get 3 over 2 times W1, and that's going to give you that vector. And then if you subtract these two vectors, that's going to give you V2. So far we have V1, which is the same vector here. We found another orthogonal vector to V1, which is W2. And if we want to find the third vector, we take V3 minus the projection of V3 over V1, which is just W1, and minus the projection of V3 over V2, which is just W2. And here also we can just put V2, W1 and V1 are the same vector. So if you put V1, that's quite all right here. And you find those one by one. So it's going to be first V3 minus V3 dot V1 over dot W1 and over W1 dot W1 and minus, then you do it with W2, so it's V3 dot W2 over W2 dot W2, and that's times W2. One more time, please be careful. These are just numbers and these are pretty easy to calculate. I did that here for you. If you write those vectors and you do the dot products, so the first vector V3 stays. That number is 1/2, and that's times W3 times W1. So it's 1, 1, 0. And the second one, again, you take V3 times W2, and that's over W2 dot W2, which we found it. And that's times W2. And if you calculate, you get 1/2 over 1/2, which is just 1. And the three vectors you have, it's those three. If you add the components out or subtract the components, so you are gonna get 0, 0, 2. So we have W1 here, which is just V1. We found W2, which is negative 1/2, 1/2, and 0. And we found W3, which is 0, 0, 2. These are the components. We're not done yet because we have to normalize that set. Normalizing, you take each vector, W1, W2, and W3, and you divide that by their magnitude. So then you get three vectors, and you can call this U1, U2, and U3. So these vectors, this last set B double prime, all the vectors are orthogonal to each other. If you do the dot product, you are going to get 0, and the magnitude of each vector is also 1. They're unit vectors. So we started with a basis just in R3, and we changed that basis to an orthonormal basis. In the next video, I'll show the general. This was in we did this in R2 and R3. We'll see how this works with other vector spaces. Thank you for watching, and have a great one, everyone. I'll see you in my next video.